Hey folks, welcome to the Talk 1 Billion Rows Challenge in Golang. Go is famous for its performance characteristics, but how fast is it really? And how does Go's performance tools make it easy for us to spot where should we optimize the code? This is Shraddha. I'm a senior software engineer at CEF, IBM. Before this, I worked on the cloud offering at Hasura. I'm also a member of the Signal, a group which is a group of independent software engineers providing excellent software solutions to different companies. I love distributed systems and databases and tinkering on puzzles on the side, which is why I'm giving this talk. So let's get into it. What is 1 billion rows challenge or 1BRC? This was a challenge introduced in the beginning of this year, 1st of January, by Gunnar Morling. A huge shout out to him. The challenge was essentially to figure out how fast can we process a huge file. The details of the challenge are that we are given a file where each line is a recorded temperature in a city, and the output of the after processing the whole file should be for each city we should have a minimum, maximum, and average temperature in ascending order depending on the city names. The challenge was initially introduced for Java, but it got caught on and engineers started solving it in different languages and comparing execution times. Since we're going to be solving this, let's talk about some of the input constraints. For each line in the file, which had a station name and the recorded temperature in that station. The file has 1 billion rows, but we're limited that only 10,000 unique station names are present in the file. And each station name can have a maximum of 100 bytes length. For the temperatures recorded, the range could be from minus 99.9 to 99.9 degrees, with the limitation that there will only be one fractional digit. This bounds the problem really well. And before we get further, I'll just recommend everyone to also go listen to the talk by Gunnar Morling himself. He's also giving a talk at P99 CONF, and you should definitely check it out. So let's get into how I'm solving this. As the talk suggests, obviously, I'm going to be using Go. Since I solved this in the beginning of the year, I used 1.21 version of Go. Since then, a lot of improvements and even the performance tools that we're going to be using in Go have landed. So you should definitely try to solve it in a much more recent version of Go. I also decided to only use the standard library packages and not use any external packages. You'll see why that is relevant later. And I decided not to use any unsafe methods in my solution. All the execution times that you see are run on my machine, M1 Pro with 16 gigs of RAM and 10 virtual CPUs. And my input file was with the 1 billion rows was around 16 GB. How I'm going to be solving this is I'll make some code changes. I'll profile the code using Go's performance tools, which will help us in figuring out what is the slow part in the code, which I'll fix again, and the loop will continue going on. Instead of just trying to do it ad hoc, I did this in a way that I'm just guided by the performance tools and what it points to. That's the process I adopted. And when I was trying to optimize these slow parts, I mainly focused on these three things, which is what better data structure can I use than the one that I'm using currently? How can I read the file in a much more efficient manner? And what are the different patterns and concurrency that I can use to improve the optimization? So let's begin. We'll start with a very baseline implementation, which is not using the most optimized data structure or isn't even using concurrency. So to begin with, I am going to be reading file line by line. For this, we're going to be using Go's scanner package with the scan method, which what it does is it reads the file contents, and then when we use scan, it rates over it iterates over the contents byte by byte till it encounters a white space, and then it returns everything before the white space, and it strips the white space as well. This is a nice beginning point where we are not doing much. We're getting the line as is from the file, and we're not actually dealing with parsing it ourselves. And for the data structure, I decided to use a simple hash map where the key will be each unique station name, and the values will be all the temperature values recorded in the file for that particular city. So that means that since we just talked about there can be 10,000 different unique cities, the number of keys possible in this data structure would be 10,000. And like I said, we're not using concurrency for the first iteration. Now, putting it all together, we're using the file sequentially, using the scan method. We get a line, we parse the city name and the temperature, insert that into the map, and then sequentially go after the map is populated entirely. We'll sequentially go over the map and figure out the minimum, maximum, average for each city. Once we get that, we'll sort everything, and that will be our final output string. So that's what we have for the first iteration. When we time it, we get our first baseline time, which is 6 minutes and 13 seconds. Okay, all right. Let's begin now, actually. So in the first iteration, I was like, let's introduce concurrency since Go has excellent primitives for it. So I focused on this last bit here where I'm going over these 10,000 entries in the hash map sequentially to figure out the minimum, maximum, and average values. I decided, okay, let's introduce Go routines for each of these cities. So we are spinning up Go routines for every single city, which will actually iterate over all of the values and figure out the minimum, maximum, and average. And then we'll put it together to get the final output string. This means that we're instantiating 10,000 different Go routines. I could have used a worker pattern here where I'm limiting the number of Go routines, but this is what I did initially. This is not the most optimized way of doing it, and you'll see how we improve it further. This reduced the execution time by 100 seconds. So now we're at the 4.5 minute mark. A thing to note is that now the Go routine count is 10,000. Profiling this code to figure out, okay, where should we do optimizations? We see that a lot of time is being spent in this read file line by line into a map. What this function is doing is it is reading the file, and then for each line, parsing the station name and the temperature recorded in it, and then inserting it into the map. So it's doing quite a lot of things. And they don't necessarily need to be done sequentially. Reading of the file and processing of its file contents can be done independently. So that's what we're going to do first. We're going to decouple reading and processing of the file contents. So this is the first bit that we're going to be focusing on in our entire flow. We're going to be adopting a producer and consumer pattern here, where the producer is responsible for reading the file line by line, and then the consumer is responsible for actually parsing the station and temperature values from it and inserting it in the hash map, as these two things can be done independently. For both of these, we're going to be introducing Go routines. So as you can see, this is a Go routine and this is a Go routine. And to communicate between these two Go routines, we're going to be using the lines channel. To begin with, this is an unbuffered coroutine. So this means that it has zero capacity. We'll see why that is relevant. When we time it, we see that it actually doubles the execution time. In the previous iteration, we were at 4.5 minutes, and now we're at more than 9 minutes. So let's profile the code and see what went wrong. As we can see in this profile, in this flame graph, this is the flame graph of the CPU profile of the code. We can see that a lot of time is being spent in switching between Go routines. We can see that a lot of time is being spent in runtime schedule and just sleeping or waking up the Go routines. This means, so what's going wrong? Channels are blocking. What we're using is an unbuffered channel. This means that as soon as the producer Go routine adds an item in the channel, it can't add any further items till the consumer Go routines actually consumes this existing line that is present in the channel. This defeats the purpose of actually making it independent since they're still blocking each other all the time. So a very simple solution to this is to increase capacity. I tried with different capacities and 100 seemed to be the most optimal one here. So just increasing the capacity to 100 and then timing the execution, we land at 5 minutes 22 seconds. Now this is reduction from what we were doing previously with an unbuffered channel, but it is still higher than where we were in the previous iteration at 4.5 minutes. So let's again profile the code and see what we're doing wrong. Looking at this, we can see that a lot of time is being spent in receiving from channel. So this makes me think, what are the number of items that we're sending and receiving from the channel? Since there are 1 billion lines in our input file, we're actually sending 1 billion items. Now, this is a lot. So let's reduce this. There are many ways to do this. To start off with, what I decided was the lines that I'm reading sequentially from the file, I'll chunk them together in 100 lines in a slice and send that over the channel instead of sending independent lines. So we initially were sending 1 billion lines. Now we're sending 10 million slice of lines to the channel. And then the consumer coroutine is now responsible for getting the slice and then iterating over the slices to figure out the station name and temperature and inserting that in the hash map. So putting all of that together, this is what iteration 2 looks like. We read the file sequentially in the producer coroutine, chunk 100 lines together to form a slice, send that to the slice channel, and then the consumer coroutine parses it, inserts values in the hash map, and so on and so forth. Timing this, we do get a reduction of about a minute, and we land at 3 minutes and 41 seconds. Now, a coroutine count went up by 2 because we introduced a producer and consumer coroutine, and the number of items sent on the channel is 10 million. Profiling the code, we see that again, a lot of time is being spent in go routine switches. Now, this makes sense because we do have 10K go routines. So let's fix it in the most easy place possible right now, which is by reducing concurrency in this last bit here, right? But let's do it in an efficient manner. Let's do it by improving our data structures. So the first data structure that we're going to be improving is that when we're reading from file in string and then parsing that to temperature, we were initially doing that in float 64. Instead of float 64, now we're going to be doing it in integer values. Doing this helps us in two ways. One, it speeds up the parsing, and two, all the arithmetic further down the line. Now, this is a classic it depends moment. It will depend on your CPU architecture, how much it helps in optimizing your code. The next thing that we're going to be doing is that we don't actually need to save all of the temperature values recorded for each station because we're not really using those independent values. We just require the minimum, maximum, and average values. So what we're instead going to be saving is the minimum temperature value found, the maximum temperature value found, and the sum of all the temperature values found and the count of them. This is like a nice summarized map. Now it's much more easier to go over it and figure out the values because we almost have the final contents in our hash map itself. So now instead of instantiating go routines, we will sequentially go over this hash map to just format the result into the final output string needed. This change helps us in two ways. First, it really improves memory efficiency. The amount of memory that we're using is really decreased because initially for those 10,000 unique stations, for each station on an average, we're storing about 100K different float 64 items in the value in the hash map. And now we're just storing 4 int 64 items. And now for go routine count, initially we had 1002, and now we just have 2 go routines, which are the producer and consumer go routines. So putting it all together, it looks like this. You can see that the concurrency is completely missing from the last bit here. And timing the execution, we land at 1 minute 39 seconds, reducing the execution time by more than 2 minutes. The go routine count is 2, but still the items sent on the channel are 10 million. So let's now read the file in chunks. in this first bit here, we're still reading the file sequentially, and because we're using scan, we're still iterating over whatever is being read twice. Once while we're reading it, and the second time when we're using scan, when Go is trying to figure out where's the next white space character and then stripping it. So instead of scan and looking at the code that is internally used in scan, it actually calls os.read. And since we don't really want all of these helper things that scanner is doing anymore, let's just directly use os.read. But now that we're using that, now that we're reading chunks from the file, and just to specify, I'm going to be reading 64 MB chunks from the file at a time. Now we have a problem. To independently process these chunks, they should end at the end of a line, that is at a white space character after the temperature recording has ended for that particular line. But there is no guarantee that when we're reading these 64 MB chunks, it is always a complete line. That's where it's ending. So we have two options. Either we can read till the next white space character from the file byte by byte, or from the whole chunk that we have read, we can go back and backtrack till the last white space character that we see, that we find in the chunk. Since we're trying to optimize this, again, introducing reading byte by byte from the file doesn't make sense. So we're going to be using the second option here, where from the chunk that we've read, we're going to reduce it down to the actual last white space character encountered, and we're going to be sending this chunk with the next chunk that we read. So this is what it looks like. Now we sort of are going towards map reduce pattern, where the producer is reading the file sequentially, but this time in chunks. Then we're actually getting a complete independent chunk where the previous leftover chunk was there. We're adding it to this red chunk, and we're removing the last non-white space characters that we've encountered, right? Which we will append in the next chunk that we'll read, which will prepend in the next chunk that we'll read. And we'll send this independent chunk to the chunks channel. So this is a new channel that we've introduced. And then we introduced a new worker go routine, which is actually responsible to reduce this chunk that we've read into the slice of lines that our code was already dealing with. And then the rest, the reducer go routine, will get these slice of lines from the channel and then actually parse it down to get the temperature and city values and actually insert it in the summarized map. But we notice something here, that this worker go routine is not really dependent on anything. Like, we can instantiate more go routines here. So let's add more concurrency. Instead of one worker go routine, now we've introduced, so I introduced 9 go routines, which is essentially the number of virtual CPUs that I have minus 1. So I introduced 9 go routines here, which will all responsible to get chunks and then reduce it down to slice of lines and send it to slice of lines channel. But now, if you notice here, what we've done is that, yes, we've improved the concurrency and have introduced a map reduce pattern, but we've increased the number of items being sent on channel. Here, we're sending items to the chunks channel, and from the worker go routines, we're again sending those 10 million slices to the slice of lines channels. So is there a way we can reduce the number of items sent on channel? Let's lean on data structures here. And instead of sending slice of lines, we're now going to be, in the worker go routines, we're going to be reducing the chunk to a mini summarized map. So similar to what we actually have in the final data structure, we're going to be doing something similar. All of the lines that will be parsed from these chunks will actually be added to a mini summarized similar to this map. And instead of sending the lines directly, we're going to be sending these mini summarized map, the maps channel. So let's see how does this improve the number of items sent on the channel. So initially from the producer go routine, because we're reading a 16 GB file and we're reading 64 MBs at a time, we get about 256 different chunks that we read and send to the chunks channel. And now worker go routines consumes it and reduces every single chunk to a mini summarized map. So that's another 256 items being sent to the maps channel, which then the reducer is going and reducing and added it to the final summarized map. So that's 512 items in total, as opposed to the 10 million ones that we had earlier. So this is a huge reduction. Putting it all together, it means that we have a nice map and reduce pattern. efficiently using concurrency to get the final summarized map, which we're sequentially iterating to get our final output string. Timing this, we finally arrive at 28 seconds, sub 1 minute execution time, and this is a reduction by more than a minute. The number of go routines now is 10. So one is a producer, one is a reducer, and then we have 9 worker go routines. And the items now from 10 million have gone down to 512. So let's profile the code one last time and see if we got rid of all of those sleeps and schedules. And we can see that after doing the optimization, we no longer see any sleeps or schedules, runtime on schedules, and we can actually see that now most of the time is actually going in accessing the map or parsing ints. And that's about it. We started with a baseline implementation of 6 minutes, and finally adopted a map reduce pattern and reduced it down to 28 seconds, all with the help of all by being guided by where Go's performance tools were pointing to improve the code from. And what are the further scope? I didn't use any external packages or any unsafe. But if we were to use any external packages, we could use maybe Swiss maps to improve the maps access and assign time, or we could use mmap for reading file as if we can use unsafe. And there are other folks who have done extremely amazing solutions as well that you should definitely read. And yeah, that's about it. Please do reach out to me with any feedback or questions, or if you folks have solved this, I would love to hear it. And you can scan this QR code to get a link to slides. And that's all. Thank you so much for listening to me.